Okay, hello. So let's suppose we have this scenario where we have this block of mass m and it's attached to spring constant k1 and k2 on separate sides. So let's say we're asked to find the period of the oscillatory motion of this block using the variables k1, k2, m, and m, right? So, in order to find the period of this function, of this oscillatory motion, we need to let's first given that given that the block is moved a distance x, like to the left. Let's assume that the block is moved the distance x to the left. So if you assume that the block is moved the distance x to the left, then we can say that the restorative force that acts on block M, and let's just draw a free body diagram right now, and this dot right here would represent mass M. So if this block is being pushed a distance x to the left, then this spring constant or whatever, the restorative force would point opposite to the direction, and it would have a total force of k1, a total restorative force of k1 times the distance x, because it's being moved x to the left, so it's gonna wanna restore its equilibrium position by moving to the right. And if we move this block a distance x to the left, right, that means we're also disturbing the equilibrium of this spring and its spring constant. And if we're moving it a distance of x to the left, it's also gonna want to move back to its equilibrium position to the right. So this spring constant, the restorative force of this spring would wanna move the block back to the right to its a natural equilibrium position. So if you represented that in the free body diagram, it would look like this: k2 x2, right? So in this scenario, we know that the net force that acts on object M or block M would have to equal to k1. I made a mistake here. Yeah, this is just mass M. Yeah. So we know that the net force that acts on object M would have to equal to k1 times x plus k2 times x as well. So if we know that the net force that acts on the object is k1 times x plus k2 times x, then we can say that x, we could just distribute this. So k1 plus k2 times x would equal the net force, and we know the net force equals mass times acceleration, right? And this equals to x over parentheses k1 plus k2. So okay, k1 plus k2, and then we could just divide both sides by m, which is the mass. So divide this by m. So you get the acceleration equals to x times k1 plus k2 over m. And we know that from simple harmonic equations, the acceleration of an object, since this would simulate like for example, if you have a pendulum here, if this pendulum swings back and forth, and when it swings back and forth, for one cycle, we determine one cycle to be when this mass over here comes back to its original position. So when it goes like this, goes here, and then comes back again to its original position, that would be equal to 1 period. And if we look at the shadow of this block, it would simulate a simple harmonic oscillatory motion for a spring. So, and knowing this, we know, using just like knowing what the centrifugal acceleration equals to in this scenario, we can say that the acceleration of this simple harmonic motion would be equal to 4 pi squared times the displacement x, the maximum displacement x, over t squared, and t would be just equal to the period, and this would equal to this function right here. Right? This would equal to this right here, and if we cancel the x's out and isolate for t, you'd eventually get that 2 pi times the square root of m over k1 plus k2 would be the period of oscillation for the simple harmonic motion. Yeah, that's about it. Okay, thank you for listening. This is the Fall Academy signing out.